Our goal is to be able to complete squares, but what we're going to do is learn this in steps. So our first step was learning the special product a plus b the whole squared. So that was part 1 of completing squares. So if we need to expand a plus b the whole squared, this is a binomial, two terms, the whole sum of two terms, the whole squared. So we square the first plus, if we see a plus here, then that would be a plus, twice the product of the two terms. So we take the two terms and multiply them together and take twice of it, plus we square the second term. This is a quick way of expanding a plus b the whole squared, and that's what we did in part 1 of completing squares. Now the next step is doing the opposite. If we are given a quadratic expression, can we figure out if it can be written as a perfect square? So let's see, we are kind of working backwards here. So we're given a squared plus 2ab plus b squared possibly, and can we go back and write it as a plus b the whole squared? So let's look at this term. So the first term is a square, it's x squared, and the last term is also a square, which looks promising. The middle term is negative, so let's put a negative sign here. Now, if this were a perfect square, then the middle term would have to be twice the product of the first term and the second term. So that would be twice the product of x and 3. Let's see what that is equal to. X squared minus 3 times 2 is 6x plus 9, and that's exactly what we have. Now if it is in this form, then we can write it as a perfect square, so that's x minus 3 the whole squared. Now I want you to think this way. X minus 3 the whole squared is x squared minus 6x plus 9. So in part 1, when we got an expression of this sort, we learned how to use the special product and expand it into this quadratic, standard quadratic form. Here we are doing the opposite. If we get the expression in this form, which is the general quadratic form, then can we write it as a perfect square? So let's do the same thing in the next example. So we are given this expression, which is a quadratic expression. We want to see if it can be written as a perfect square. So let's see. The first term is a square, which is good. The last term is also a square, a perfect square. So this looks promising. The middle term is a negative, so I'm going to put a negative there. If this were a perfect square, the middle term would have to be twice the product of the term here and the term here without the square. So there would have to be just the x and the 7. They need to fit in here. So let's see, if we put an x here and a 7 here, let's see what that works out to be. X squared minus 14x minus 49. So that's perfect. That's exactly what we have. Now this tells us that the expression is a perfect square. So the first term is x, the sign is negative because the middle term is negative, and the last term is 7 the whole squared. One more example. We're given a quadratic expression. We want to see if it's a perfect square. Let's see the first term, that's a square. The last term is also a square. It looks promising. Let's put the negative sign. What would the middle term have to be in order for this expression to be a perfect square? It would have to be twice the product of these two terms, x and 7, without the squares. So we want to put this here and this here. So that is x goes in the middle as the first term, and the second term is 7. So that is x squared minus 14x plus 49. Now, do you see that the first and last term were squares, and it looked promising. It looked like it was going to be a perfect square, but the middle term would have to be negative 14x for it to be a perfect square. In that case, it would be x minus 7 the whole squared. But look at the term that we have here. The expression contains a negative 16x, which means this expression is not a perfect square.